In this lecture, we covered numerical integration. And the main goal that we had throughout the entire lecture is to approximate the integral of a function f of x on the interval from a to b using numerical methods. We started out with some applications of integration and of definite integrals. And the main application is actually the primordial example related to the definition of such an integral is to compute the area below the graph of a function. Quickly, we learned that analytical integration is often impossible or very hard to do. So numerical integration is often the only way that you can compute such integrals. We discussed several numerical methods for integration, and we started with these Newton codes type methods, in which we fix a number of points on which we will approximate the function f of x using a polynomial of a certain degree. And examples of the methods that we saw were the rectangle methods, midpoint methods, trapezoidal methods, and Simpson's methods to close off. In addition to this, we also discussed Gauss quadrature, which had a slightly different strategy in that we approximate the integral directly as a weighted sum of function evaluations at specific points with corresponding weights. And both the points and the weights were free to be determined in order to attain an accuracy that is as high as possible. The weights and points were determined by stating that the integration rules should be exact for polynomials up to a degree which is as high as possible. We discussed some MATLAB built-in functions, namely the traps function that allows you to apply the trapezoidal method for a set of data points that are given to you, or the integral function that allows you to easily integrate an analytical function over a desired interval. And this integral function applies a specific Gauss quadrature rule. In the final video for this lecture, we discussed errors in numerical integration. We derived how the error can be quantified for both the midpoint and composite midpoint rule, and showed that this composite midpoint rule is of second order. So it's proportional to h squared, where h is the width of the subintervals. We also saw that the accuracy of different types of Newton codes methods ranges from first order for the rectangle method up until even fourth order for Simpson's methods. Finally, we also saw that Gauss quadrature is extremely accurate in that adding only a single Gauss point allows the error to be reduced by a factor of 100 to 1000 for smooth functions.